Hello and welcome to this video lecture series on microprocessors and microcontrollers. And this is the 26th video lecture, and we are studying the microcontroller 8051. So in the last lecture, we had started 8051 and we were trying to study the architecture of 8051 there. And we studied some major portions of the architecture. However, the architecture of 8051 is very vast. I mean, vast in terms of various subcomponents that it has got. So, it would help us if we understand these addressing modes prior to understanding the remaining portion of the architecture. I mean, by studying these addressing modes, we will also get an idea of the internal hardware components of 8051 also. So, that is why in this particular lecture we are going to study addressing modes. And now in this lecture we will be primarily focusing on the internal addressing modes. What do I mean by internal addressing modes? In 8051, as we know that there is some internal RAM and ROM which is available, and we can externally interface 64 kilobytes of RAM as well as 64 kilobytes of ROM. So we are not talking about those external RAM and ROM in this particular lecture. We will only talk about the internal memory that is available to us and how the addressing modes work in that case. So we are only going to address that particular case there, right? So in the previous lecture, we have started with this architecture of 8051. So let me just show you that for a quick revision. So we said that the 8051 is a microcontroller and it is fabricated on the same chip, including its CPU, its interrupt control structure, oscillator, then internal ROM and RAM, timers, serial control, IO ports, and bus control. So it's a microcomputer system in itself, right? And we also distinguished between a microcomputer and a microcontroller. Microcontroller means a microcomputer on single chip, and microcomputer means brain as well as peripherals on the same system, right? Not necessarily on the same chips. So they all should be connected. Then we saw the family of 8051, and there were different options available for RAM, ROM, timers, interrupt sources, IO pins, etc. So depending upon your choice and your work, you can select a particular microprocessor. Then we saw the internal architecture. We saw various diagrams for that. So we have input output ports which are available from port 0 to port number 3, a total of 4 ports. Each port is bidirectional, and we have 8 pins on each port, and it has got its corresponding latches. Then you have got ROM, and you have got RAM, in which special function register RAM is also considered as a hardware part of that RAM. But you essentially have got only 128 bytes in RAM, right? So however, ROM is 4 kilobytes. So it's a huge difference. I mean, RAM is only 128 bytes and ROM is 4 kilobytes. So this kilo is a huge number as compared to 1. So we have great ROM here. Then you have got program status word, which is of 8 bits, and we have seen the format for that. Then you have got program counter and DPTR. So program counter is used for code purposes and DPTR is used for data memory purposes. So we have elaborated on that also. And this is the structure of RAM that you see here. RAM has got bank 0, bank 1, 2, 3, and some bit or byte addressable area, and then some special function registers also, right? And we also saw the pin diagram for 8051, and we discussed the meaning of all of these pins there. So this was also one of the diagrams that we saw on the last turn, right? Then this is the structure of the flag registers, and here RS1 and RS2 were important bits because they were used to select bank 0, 1, 2, 3. So we will see the usage of RS1 and RS0 today in selecting a particular bank. Then we stopped there, and we will continue with the further architecture portion later. But to be able to understand this RAM completely, this is the RAM, first 128 bytes of RAM. We say that only 128 bytes are available in RAM, but some people also consider this a special function registers to be a part of this RAM. So that way, these both, when they are combined, it becomes 256. But one important point to note is that in these special function registers, only 21 of them are available out of this 128 bytes, and rest of the bytes, they are not used for any purposes. So they will they are not actually used, they are not actually present physically on the hardware, so they are not used for any purposes, right? And the purpose of current lecture is to be acquainted with all of these, because here RAM is not simple. I mean, in 8085 and 8086 we had a simple memory chip, and each location of that chip was able to store 1 byte of data, and that 1 byte of data, it is same for, I mean, every location of the RAM. Every location of the RAM had 1 byte of data storing capability, and it can be used for any general purposes. But here the RAM has a particular structure. So before going to the further details of architecture, today in this lecture, let us try to understand how these things actually function, right? Because if we do things, we will remember them better. So this is the idea for this particular lecture. So let me just begin by showing you the emulator that we are going to use. So the emulator that we are going to use is this one, and it is an open source and free emulator. So the name of that emulator is EDSIM51SH. So you can search by this name on Google and you can reach to its website, and from there you can download it. It is free for usage, so you can use it for your purposes. So what you see here on the left is the programming model of programming model of 8051, right? So let's first get acquainted with the interface, and then we will talk about this RAM that you are seeing here, right? This RAM that you are seeing here, we'll talk about it, what all it is doing, right? So let me just quickly help you understand this interface. So this is the area where you will be writing your codes, and you can directly start writing here. After writing, you can just press the save button and save it to some location. Or if you want to load a pre-written code, you can load it by using this button, right? So these two buttons are very primary, and rest of the buttons will be discussed when the time is due. So on the left, you will see the programming model of 8051, right? So here you can see, let us first begin with the accumulator register, ACC or A register. This is the accumulator register. It is written here, right? Then you have got B register also, which is also a general purpose register. And sometimes it is busy with timer calculations. Otherwise, it can be used with accumulator register for accomplishing various tasks, right? Then you have got this program status word. This program status word is also elaborated here bit by bit, because we already know that this program status word has got 8 bits, and the meaning of those 8 bits was very clearly illustrated here. Parity, then this is of no use, which is reserved bit, then overflow. RS0 and RS1 were used in bank selection, and this F0 is user programmable bit, and auxiliary carry, and then carry. So for today's purpose, please remember the positions of this RS0 and RS1. So B3 and B4. So B3 and B4, if you start from 0, B3, that is bit number 3 and bit number 4, are used to make a particular bank selection, right? So that's what we are going to see. After that, in this particular thing, we have got IP and IE. Then PCON we have discussed yesterday, IP, IE, etc. also. Then this DPH and DPL. These are the portions of your DPTR, higher order bit and higher order byte and lower order byte of data pointer. So they are present here. Then you have got stack pointer, and you can see that by default it is initialized with 07. So stack will start filling from 08 and onwards, right? So this is how it is designed. So this is your stack pointer. Rest everything is initialized to all zeros, right? Now after that, you can see that here you can see registers from R0 to R7. So these are the registers. These are the registers of bank 0, because by default bank 0 will be used. We have seen the structure of RAM. Let me again show you that structure. These bank 0, bank 1, bank 2, and bank 3 were there, and we said that individual banks had 8 registers. So bank 0 is used by default, right? So these are the 8 registers which starts from R0 to R7 for bank 0. If you want to select another bank, then you have to set the appropriate bits D3 and D4 in the program status word. So this is the elaborate form of program status word. And here you can see that this is D3 and this is D4. So you have to set it, and we will see how to set or reset it when we will understand it through a simple program. So accordingly, these R0 to R7 will become the registers for that appropriate bank, right? Whichever bank is selected. Currently, they represent the registers R0 to R7 of 00 bank. That means bank number 0. When we will change it to say 11, then they will become R0 to R7 will become the registers of the corresponding bank. So you won't see four such illustrations here. The same illustration, depending upon these two bits, can be used for the corresponding bank. Then you have this TH0, TL0, and TH1 and TL1 for timers. Then you have this T mod, that is timer mode and timer control. So we will study these when we will study the topic of timer. You have a program counter here. So program counter is of 16 bits. So you can see that it is of 16 bits. The corresponding register for program counter is also DPTR. So DPTR, we have already said that it is present here. Then you can see that you have got these SBUF pins. So read and write operations are also there. Then reception and transmissions in case of serial control. So SCON bit is SCON register is also there. So we will study this when we will study the serial communication. So we will study all these pins at that particular time. And this is the RAM structure. So you can see that it begins from 00 and it ends at 70F, right? So last location is this is 70 and that is F. So 70F will mean 127. So it starts from 0 and ends at 127. So that simply means that you have got 128 bits. Sorry, 128 bytes, not bits. So every location that you see here is a byte, and the double zero, it represents actually two hexadecimal zeros, as was the case with 8086 and 8085 also, right? So this is a general picture here, and on the right side you can see you have got these ports. So port number 0, which is also having 8 bits, port number 1, port number 2, and port number 3. So we have already said that the data bus is interfaced with this port number 2. So they have shown these connections DB0 to DB7 here. And we already know that address bus is also interfaced with this. The lower portion of this address bus is interfaced here. So it is not shown, but it is understood by us that it is present there, right? So this is the general programming model. And now through a simple program, we are now trying to understand how things move in this. Because if we understand how things move from here to there, our understanding of the architecture of 8051 will be further strengthened. So that is the whole sole aim for today. Now, another important point to note here is, let me just show you this diagram. So in this diagram, you can see that if you talk about the accumulator register, so this is ACC or simply A or the accumulator register. This accumulator register also has got some address, and its address is 0E0H. H is for hexadecimal and E0 is the actual address. 0 is appended because it is customary to write 0 before a number which does not start from a numeric digit, right? So it is starting from E, that is why we are writing 0 here. But the important point to note here is accumulator has got some address. So this is the address of accumulator. Now this thing was not present in 8085 or 8086. I mean the accumulator register there. If we talk about 8085, we have A, B, C, D, E and HL registers there. So they did not had any address. They were internal to the CPU and they did not had any address. But here the point of difference from the earlier microprocessors was that even accumulator and every other register that you talk about, be it accumulator, B register, program status word, instruction pointer, or port number 3, that is P3, IE, or port number 2, or serial control, or port number 1, or timer control, or port number 0, they all have got addresses, right? And their addresses, they are shown here, right? So these are the addresses for these particular registers. They are internal to CPU, but they have got addresses. And because of that, they can be either accessed by their names, like accumulator can be accessed by mnemonic A, and Alternatively, it can also be accessed by this address. Now, what is the point of providing this address here? We will see it that it is necessary because in 8051, uh, we will also study pointers, right? So you can either refer to the accumulator by its name A, or you can just keep its address in some other register, and those other registers are only R0 and R1, and you can manipulate the data which is kept in the accumulator register, right? Another important point to note here is if you see all of these registers, their individual bits have also got certain addresses. So their individual bits, they also have addresses, and it is written here. These addresses are written with the corresponding bits. If we talk about program status word, then D3 and D4, as we know them by this name, they will be used as it is in programming, and we can change this D3 and D4 bits to select one particular register bank. So every memory location of one byte has got its address. So this is the byte address, and the individual addresses that you see here are the bit addresses, right? So this way you can also access your accumulator bit by bit, or any register for that matters. And similarly, if you talk about this bit addressable area here in the RAM portion, so you have got these addresses which are byte addresses, and here you have got addresses which are bit addresses. Now, a confusing thing here is you can see this 21H here. 21H is the byte address. This is the byte address for this complete byte. But you will also be able to see 21H here. This is also 21H. So how does this microcontroller distinguishes between this 21 and that 21? So we will see later in the programming portion that these are the addresses, and these addresses, they are used with different set of commands. For manipulating these bits we have different commands, and for manipulating bytes we have different command. So if we write 21H with a byte instruction, its meaning will be this complete byte, and if we write this 21H with a bit instruction, its meaning will be only this bit only. So there are these addresses which are same, but they belong to different instructions, so that way they can be uniquely deciphered or uniquely decoded, right? So these are some important points which we need to keep in mind before we go to the programming portion. And let's now start some small programs in this 8051 to be able to understand the complete scenario. So I have already written the program, so let me just load that program. So I will load it from my desktop. Let me find my program first. The desktop is, this is written in Java. This software is written in Java. So finding desktop is really difficult here. Okay. Users and then desktop. Yeah. And here the name of my folder that I am using is 8051 programs. Yes. So I'm using this file program1.asm. So yeah, this is my program, and through this program we are going to understand a lot of things here. So the first topic that we are going to study is data movement. You will be surprised to note that microprocessor rarely performs the operation of uh, addition, deletion, subtraction, and logical manipulation, etc. Most of the times, this microprocessor or microcontroller is involved in data movement operations, right? So, calculations are very few or slim as compared to data movement inside either a microprocessor or a microcontroller, right? So it is important for us to study the data movement instructions, and if we study the data movement instructions, the architecture will become more clear to us. Now, let's first start with immediate addressing mode. So here we have got addressing modes. Let's first see their names. First is immediate addressing mode. Then there is this register addressing mode. Then you have got direct addressing mode. And then we have got next is indirect addressing mode, right? So these four addressing modes will be discussed today together with some additional and important concepts of programming, right? So let me start with this instruction first. Move a comma hash 23H. Now, an important point of difference between the microprocessors that we have read up till now and this microcontroller in perspective of programming is that if you want to move immediate data, then you have to use a hash before that, right? So there is, if you just want to move this 23 into this A register, you have to use a hash before that. Why? The reason is this. Let us again look at this particular program. Oh, sorry, this particular diagram. In this diagram, you can see that there are byte addresses as well as bit addresses, right? So if you remove this hash, if you remove this hash and you only write move a comma 23h, it will mean that the value at address 23 will be moved to A register. And what is the address 23? So this 23, you can see that this is this complete byte. So this complete byte, whatever the value of this byte is, I mean, there will be 8 bits, of course. So those 8 bits will be moved into the accumulator register. So that will simply mean that. So if you want to use value, then you have to use a hash before that. Otherwise, whatever is written here, it will be treated as address. So primarily, if you do not put a hash before any number, it is treated as a address only. And through this command, I simply want to move this 23 value into this A register, right? So let me first just assemble this, and we will try to run it step by step, and we will see the corresponding changes. So here I have assembled my program, and after assembling, you will see that the assemble button has changed to step button. So by pressing this step button, I can execute this program line by line. And here you can see the addresses at which these uh, program lines are written inside our internal ROM or the read-only memory. So these addresses are not in regular order, I mean 0 2 5 7. So this does not follow any order. It simply means that from 0 to location number 1, this address, this instruction is stored. So this indicates how many byte it will consume, right? So these are the addresses, ROM addresses, where our program is stored. And now we are on this red line. So if I will press this step button, then this line will be executed. So you can see that the accumulator, it will contain a value of 23. So this is accumulator and it will have a value of 23 once I execute it through one step. So let me press this. I have executed it through one step and 23 value has been moved into accumulator. If you'll press run, then this entire program will be run at once. But I'm not doing that because we want to study it line by line. Then similar to this instruction, you can also move data into B register also. And the syntax that you follow for this number ff or any number that begins with a non-numeric digit is that you have to put a 0 before that number. So mind it that 0 is typed as phi in this particular thing. So you will press 0, but it will be looking like this. So don't be confused with this. This is simply 0. This is not phi here, right? So if you will type 0, it will look like this. So let us execute this also. This is also a very simple program, a simple line to run. So step, and you can see that inside B register, your value of FF has been moved, right? After that, there is this instruction move R0, comma, hash 12H. So you can just use this register R0 and move a value of 12 into that. So let's try to run it. So you can see, sorry, let me move one step. Yeah. So a value of 12 has been moved to R0 register. Now there are 4 register banks. So which R0 has been used? The R0 for which these D3 and D4 have been demonstrated here is this particular R0, right? So if you will change these bits, then this R0 will disappear and that this R0 contents will be changed and it will become 00 because nothing has been done to other registers as of now. So we will come to that later. And similarly, you can also move a 16-bit value to the data pointer, DPTR, right? So this H indicates hexadecimal. So these are all hexadecimal digits. So let us also run this. So if you press this, you can see that inside your data pointer, the higher order byte will contain 56 and the lower order byte will contain 78, right? So lower order byte 78, higher order bit is 56. So this is what has been done here. So this is immediate addressing mode, and we all know what immediate addressing means. Whatever data you want to move is directly available as the part of the command that you are writing. So the microcontroller does not have to go anywhere to fetch the data. So it does not require any address as such. The operand is available in the command itself, right? So that's what we mean by immediate addressing. So there is nothing much to explain and understand here. Let's move on to the next mode, which is called as register addressing mode, right? So inside this register addressing mode, you can make a transfer from and to the register, right? So you can see that there is this instruction move a comma r0. So now r0 contains 12 and a contains 23. So after the execution of this instruction, the value of r0 will be copied to a register. So this 12 will be moved into the a register. So let us execute it. So you can see that accumulator now contains a value of 12. Similarly, you can do it in B register also. So let me just do it. So in B register also the same value has been changed. You can do it like reverse ways also. Move R1 comma A. So R1 now has a value of 0 0, and whatever is the value in this accumulator will be copied there. So you can see that R1 also now has a value of 12, and you can also move the value from A to B, although they are already the same, but you know that internally the value will be copied there. So this is also very simple. It is called register addressing mode on the simple grounds that the operand that has to be copied into the source register, or the destination that has to be copied in the source register, that destination is present in one of the registers, right? So this is the register addressing mode. So these two modes are pretty simple. Now let us move on to something which is called as direct addressing. So before going on to this direct addressing, let me just move a value of 76H into the register R1, because here now R0 and R1 have the same values. I want them to be different. So this you already know that this move R1 comma hash 76H is immediate addressing mode. That is why I have written it prior to direct addressing mode. So it is just for initializing the R1 register with some different value. So let me just execute it. Now you can see that this R0 and R1 registers, they have got different values. So what do I mean by this direct addressing? In direct addressing, what we are going to do is we are going to use the addresses instead of names. What do I mean by that? Let us again look at this particular diagram. So here you can see that accumulator has got the name A and its address is 0E0H, right? So in direct addressing mode, we are going to use the direct addresses. I mean the addresses of the registers that you have here, right? So let us begin by simply putting something into a register, right? So here you can see that I have written this command move, then E0 comma 89, right? So this E0 0 is appended before this because it begins from an alphabet instead of a numeric digit, and H is for hexadecimal. So E0 is the number that we are writing here. Move E0 comma hash 89H. So this hash 89H is immediate data, right? But we are using this address. So let us see at this address what is the register that we have got. So that 0E0H has got the name as accumulator. So here on executing this particular command, 89 will be moved to accumulator. Now this is very different from 8085 and 8086. So let us just step it over and see if it happens or not actually, right? So here I have run it and you can see that accumulator now contains a value of 89. So some programmers, they prefer to use these numbers instead of directly using the names of the registers, right? So these numbers can be used. Similarly, you can also move into the accumulator the value of register R1. So you have got this register R1. So whatever I am saying about this R0 and R1 is also applicable to all of the other registers. So let us see, R1 has got a value of 76. So after execution of this particular command, that will come into the accumulator. So I have stepped it over and you can see that 76 is in the accumulator now, right? Now let us see this command 8ch comma 91h. Now what is this 8ch? 8ch is this th0. So let me see here 8ch. So where is my 8ch? This is 80. Okay, let me find that address because even I forget where these numbers are when I have written this program. So, do you see TH0 anywhere? Okay, so let me just see it from here. This TH0 for TH0, the address is 8CH, right? So you can see that this TH0 is there and its address is 8C, 8C in hexadecimal. So if it is present here, let us see it here, or otherwise we will go with that address only. So pcon, yeah, 8C. 8C, this is the bit address, but I can't see any byte address here. But anyway, if it is the byte address of th lower and th higher, etc., so it will be moved there. So this 8C is the address of th0. I might have seen it from some other reference, but if this is the address, then this data should be moved there, 91. So let me execute this command, move 8ch, and let me see if 91 is moved into this th0. So if it is done, then this is the actual address of that. So yes, 91 is moved there. So this 8C is the address of this th0. Similarly, you can also send the data of R1 to 8ch. So let us run it. So now the data of R1, which is 76, has been copied here. So this is what we mean by your uh, direct addressing mode, where you are using the direct addresses of the registers, right? So another important thing to note here is that you cannot write like this, move r0 comma r1. So a transfer from register to register of one bank is not possible with direct names. It has to be done with their addresses. So let's see what is the address of r0 and r1. So this R0 and R1 for bank 0, they have got address of 00, and after that there will be 01, right? So you can simply write it like this, move 0 comma 1. What will it mean? The 0 is now an address, right? And since it is written with move, so move expects you to write a byte address. It never expects you to write a bit address. So 0 and 1. So 0 and 1 are the addresses of the registers number 0 and 1 of bank 0, right? So if you see this diagram, if you look for registers R0 and R1 in bank 1, the addresses will be different. They will be 8 and 9, right? But for bank 0, they will be 0 and 1. So that's what we are trying to do here. And through this particular command on execution, the data from register number 1 will be copied to register number 0. So you can see that these two will have same value 76 after its execution, which is also true. So 76 and 76. So the value has been moved here, and you can also do the vice versa. So let me just step over it. So the value is copied. So this was unnecessary because anyway they had the same data. So you can do it anyways, and with any of these registers. So this is how your direct addressing mode works. In direct addressing mode, you can just put the direct addresses of the RAM structure that you are seeing here, and every register that you see here has got a name and address, and with move instruction the byte addresses can be put. We will talk about these bit addresses that you see here a little later, that can also be done, right? After this, let us now move on to indirect addressing mode. What is indirect addressing mode? This is what we mean by pointers. So from here, the concept of pointers begin, right? So before studying this mode, let me initialize this R0 with F0H, right? So let me just execute this command. So I'm initializing it on purpose to just make these things different, 76 and F0. So these two are not different. Now, indirect addressing mode, in that what happens is one register, which is either R0 or R1. Now I am not talking about all the other registers. So this indirect addressing mode is only applicable to R0 and R1 registers, because these two are pointer registers and they can hold the address of some other register that is present inside this microcontroller, right? So whatever I am saying now is only applicable to R0 and R1, and I have written it here also. R0 and R1 can be used as pointers, right? So the syntax for doing this pointer operation is like this: move, then at r0 comma hash 56h. So we are trying to move our immediate data into at r0. So what does this at r0 means? This at r0 simply means whatever is the value which is written in r0 register, you treat it as an address, and at that particular address you write 56H, right? So currently your R0 register has a value of F0, right? It has got a value of F0, and at F0 you want to keep a value of 56, right? So how do you recognize this value of R0? I mean, R0 has a value of F0. So let me search this F0 value here. So this is 00, and if you see here, this is F. So this is 0F, right? So F0, let us also see here if it is the address of something. So can you see that address here? I guess, yeah, 0F0. 0F0 is the address of B register. 0F0 is the address of B register. So what we have done is, inside R0 we have kept a value of F0, and F0 happens to be the address of this B register, which is now currently having a value of 12. After execution of this command, a value of 56 will be kept into the B register. So let me just step it, and you can see that a value of 56 has been kept at this location at the rate R0 or at R0. At R0 will simply mean that R0 has to be treated as a pointer, and a pointer simply means a register which can hold the address of another register, right? So that's what we have done. R0 is now containing F0. F0 is the address of B. So R0 is a pointer which contains the address of B register, and 56 has been moved to it. It could contain the address of any other register that you see here for that matters, right? So this is why we call this mode as indirect addressing mode. And you can also do the reverse, that is, you can put R0 on the operand side, and instead of this R0 here, you can write accumulator or B or whatever you want to use. So this is the indirect addressing mode, right? Now, so these four addressing modes are there. You can explore them more for all sorts of combination that can be used. That is, can you do it from register to immediate value to register, and vice versa. So you can search all those possible valid combination, and that will be done when we will program a lot, right? So these are the four addressing modes, and addressing modes: immediate addressing mode, then register addressing mode, then direct addressing mode, and indirect addressing mode. So these are the four addressing modes here. Now let us learn some additional concepts which are mainly related to bit operations, right? So in this thing, we have seen that this memory is byte addressable as well as bit addressable. Now we are going to use these bit addresses that you see inside both of these blocks to be able to access these individual bits, right? So let us now begin with selecting the register banks. So currently you can see that these values are applicable for 00 combination. 00 means bank 0. Now let us suppose that I want to move to bank number 11, that is bank number 3. If I want to move to bank number 3, then what I have to do is I have to set this bit D4 and set this bit D3. So how will I do that? So the command is very simple. Set B. Set B means set bit. Set bit D3 and set bit D4. So that will set these two bits, right? And after setting, what changes we will notice? These registers will all become 0. Why? Because we haven't used the bank number 11, that is bank number 3 as of now, and all the values are all initialized to 0. So let me just execute this. Okay, so before changing these banks, let us just see these two commands also. So set B 16H and clear 16H, right? So let's just see these two commands. So can you just figure out which is the 16th bit here, right? Which is the 16th bit here? So let's see this diagram first. In this diagram, if you see that the 16th bit, it is present somewhere, I think here. Yeah, this is the 16 bit. 16th bit is present here. So if you see, all the memory is by default initialized to 0. If you will set this bit equal to 1, then what will this number become? 0100, which is the first nibble or the upper nibble, and the lower nibble is all zeros. So the byte that will be placed at 22H, it will be 0100 and 0000. So in hexadecimal, it will be 40. So 40 should be placed at 22H after the execution of this particular command. Set bit 16H. Setting means making someone as 1. So 22th location, this is 20 location and this is 2. So 22th location should become 40 after the execution of the set b 16H command. So let us see that. Yeah, it has become 40. So that way only one bit has been set. But here you can see that complete byte in hexadecimal. So you are actually able to see it correctly because by setting that one bit, the combinations should become 40. We have just discussed it. And if you want to clear that bit, so you have to write CLR 16H. So let us just step it over, and you can see that that bit has been again reset, right? So these are the two commands used for setting and resetting of the bits. Now we are going to use the same commands of setting and resetting to be able to set or reset this program status towards D3 and D4, and we will see the corresponding changes in this bank, right? So first we will set this bit D3 and then this bit D4. So up till now, this 00 bank is selected. Now let's just move one step forward. So one step has been executed, and you can see that the content is 01. So this 01 corresponds to bank 1. So bank 1 means all of the registers now refer to bank 1. So you can see that all of them have become 0. Now we will move one step forward. So now this has been executed. So these both bits have been made as 1, and now this refer to bank number 3, that is 1 1. So this is how you can change banks by using this setb command. And if you want to go back to the original bank, so you can just clear both of these bits. So let me just step over these two things, and you can see that you have returned to the same pair of same set of registers for this 00 bank, right? So that is how you can select and change your banks also. Uh, After that, let us talk about input output ports, right? Bank selection is done, and now let us talk about this IO ports as a whole. That means I already illustrated that input output ports, they can be used as 8-bit ports, bidirectional ports, or you can also use their individual bits. So first we are going to learn how to use the port as a whole, as a byte. So for that, what you have to do is move P3. P3 means port 3, and you can put any binary value here, right? I have written it in binary. You could have also written it in hexadecimal. And after the execution of this command, you will see here that this port number 3, it will have value 10101010 and so on, right? So the value that will be moved into this P3 register, let us see that. So I've stepped over it, and you can see that it has got a value of this port number 3. It has got a value of this 010101 and so on and so forth, right? So if you start reading it from the MSB, it is 1010, which means A, and then again 1010, which means another A. Now, if you want to read this complete port, into some register, say R2, then that can also be done by this simple command move R2 comma 0B0H, right? 0B0H, which is the address of this port number 3. You can just check it here. So this port number 3 has got the address 0B0H. So if you use this particular command, then let us step over it, and you can see that inside this R2 register, now this R2 register has a value of AA because we have this 1010 and 1010 combination here. So both of them happens to be A. And it is not necessary that you write address here. You could have directly written this port P3 also here, but just to illustrate that this is also one of the possibilities in direct addressing mode, you can do that, right? So this is the immediate addressing mode. This is the direct addressing mode, right? Immediate because it has got immediate data here, and this is your direct addressing mode because the data which was to be moved, its address is directly given here. So you can pick up your data from here and move it to R2. If I would have written it in the reverse way, move this address and then comma R2, it would have become register addressing mode because the data which we want to pick up is present in one of the registers, right? So that way you can just access these ports. So you can just write something to the port and read something from the port. Both ways are possible, but this is when you are accessing ports as a whole. You are not accessing them in bitwise fashion, right? So now let us try to access those ports in bitwise fashion. So to be able to access the ports in bitwise fashion, you should keep in mind that carry register will be used, right? So carry register, it's present in program status word. So let me just again show you the program status word and its format. So this is your program status word, and you can see that bit number 7, or the most significant bit, is for this carry, right? So now before using that port, let me just clear that bit, right? So you see this port number 2. So this port number 2 is here, and the 0th bit, you can use this syntax P2.0. So P2.0, you can see that all of the ports have been initialized with 1 already. So now you can, what you are going to do is you are going to clear this P2.0. So it will become 0, right? So through this command, that will be cleared. After clearing that, uh, since this value has been changed, now you want to read that cleared value into some register, and that register can only be C register, not register, actually a bit location. So this bit location, which is this one, will be shown after that, right? So let me execute this command first. So after execution of this command, you can see that this P2.0 has become 0, and now I want to read this somewhere. So that can be read in this carry flag. So let me just step it over. Now you can see that this value has been taken in this carry flag, right? So it was already 0, but it has been taken into this carry flag. So alternatively, what we can do is we can just set this thing and take the value there. So let me just, instead of doing this, let me just set it and let us do it there. Let me reset this code first, and after resetting it in my actual code, let me change it to, in place of clear, let me just change it to set. So this is set B. So we will set it. It is already set although. So we will set it. So let me assemble it again. And let me just do step-by-step procedures again. Yeah, so this bit is already set, but through this command we are again setting it. So this has been set. Now this set value will be moved to this carry flag. So that's what we are intending to see. So let us step it over. Um, and now we want to execute this to see the effect of that. So yeah, this carry bit has become equal to 1. So it has picked up the value from here, right? So this way you can just access any bit of any port, and you can use it your way. So it is bidirectional. You can either take or give the values either in bitwise fashion or as a single byte fashion, right? So the last thing that we want to study today is move C, comma 23h.0. This is for the port. Now, this is also very important. Let us see what is 23h.0. So, in this diagram, in this table, where is this 23? So this is 23, and dot 0, it will mean this particular location. This is 23, this is 0. So this will mean this 18th address. So whatever is the value of the bit here, it will be used, right? So let me just keep this value. I mean at 23h, this 23h, let me just make it as 1, right? So let me just make it as 1. So what will be the content at 23h? So this is all zeros. I mean the upper nibble is 0, and let me just make it 0, 0, 0, 1. So let me keep a value of any value such that this value can be accessed there, right? So let me keep a value of 0 and all ones. So that will be 0 and f. So at 23h, at 23h, address is 23. So let me keep it as 23 here, and let me keep a value as 0f here. So this is 0f here, right? And now at 23h, whatever is the value, it will be moved to the carry register, right? Let's not keep it as f, let us keep it as 00 only, right? Or let us keep it as let's say A. So A will be 1010. So the last bit will be 0. So this carry flag is already 1. So after the execution of this particular command, that 0 bit will be copied here in the carry flag. So let me just step it over. Yeah, so that bit has been changed. It has been changed to this thing. So this is how simple operations within the registers, internal registers, and this RAM of 8051 can be made by us. And an important point to note here is that we have in today's lecture only addressed the internal addressing modes. For being able to access the externally interfaced RAM and ROM, we do not have this move instruction. We have move X and move C instruction, right? So we will talk about move X and move C instruction, not this move C. That move C is move with no space C. That means it's a complete one thing, move C. So we are going to study that when we will study more programs. So this programming portion was essential for strengthening our understanding of this 8051 architecture. And one important point to note is that after the execution of this complete program, you won't ever see any halt statement in microcontrollers. Why is that? Because usually a microcontroller is, attached to any of your appliances like washing machines and ACs. And whenever you start the computer, you do not want the program to execute and just stop. For example, if it is the air conditioner, it has to continuously sense the temperature. If it is a washing machine, it has to continuously sense various parameters related to washing machine, like washing temperature or maybe the motor speed or whatever is there, right? So we do not ever halt that complete program. You can put that program to rest or at sleep mode, but you never halt that. So these programs are usually written in loops, right? So that is why you won't ever see a halt statement here. There is no halt statement in this programming, right? So this is a general introduction to the programming model as well as to strengthen our understanding of the architecture and how data is moved in bit and byte fashion through ports, etc. And you can see that how easy is it to access the ports here. In case of 8085 and 8086, it was difficult to access the ports because first of all, you had to interface a particular IC which will help you interact with the external world, right? So that requires hardware connection as well as another set of programming through in and out instructions. So here it is easy because in microcontroller everything is present within the same chip. So you have these ports which with which you have interacted today. And in coming lectures we are going to see this serial buffer and your timers, etc. also. So serial control also. So everything will be done within this microprocessor. So this is definitely a better device if you want to achieve some specific task here, right? So this is it for this particular lecture, and I would see you in the next video. Thank you for watching this.